So I've got my coils right here. Mu naught's constant. It has a set number of coils. It has a certain length to it. It has a certain area right here. This is dependent upon how that thing is made. That we will use a capital L for. And so we get negative L di dt. This L here is inductance.
Is it the same L that we were just using in reference?
Using where?
For inductance, is that the same? Never mind. Never mind.
It is not the same L as this.
No,
Okay.
not that one.
The lowercase l, is that like the actual amount of wire distance-wise going around, or like the height of the solenoid?
It is the length.
So just like this distance, not the actual. Like
Correct,
you
right.
guys-
It's this distance this way.
Okay.
Yeah, not the length of the wire itself.
Gotcha.
Questions to hear? And what the inductor does is if I put it into a circuit, it's going to basically slow down the rate at which the current goes up. Similar to a resistor, except the resistor is actually pulling energy out of it. This is really pulling energy out. It just slows down without doing that. And I'm sure there's more sophisticated ways that the electrical engineers in the group will eventually come upon and will go, oh, of course. So let's take a look at it, what physicists like to think of as an interesting circuit. Now, I do my inductors with a bunch of loops like that. Some, I've also seen that some inductors done with looking more like that. Kind of like a transformer, or half of a transformer. So I have some capacitance, so I have a charged capacitor, so the problem starts, we zoom in, coming back from commercial, that fully charged capacitor. Capacitor at time is equal to 0. And the question is, what will the charge on the capacitor be with respect to time? And I need to do a quick glance, because what I don't want to do is get a minus sign in the wrong spot and then have to go back and fix that. Okay. Sorry. So let's make this a positive side and a negative side. I'm going to apply Kirchhoff's rules. I know that if I start at some point, working my way around, I'll end up back where I started. So if we start here and just work our way around. So I'm going to start with generically, the change in the voltage across the capacitor plus change in the voltage across the inductor is going to be 0. All right, so you were saying, Devon?
Because you're starting off from negative, so you're, I guess, losing. You're losing charge if you start from negative? I'm sorry.
Well, we're going to be, we're definitely going to be losing charge, because as soon as we start this thing, the electrons on here want to flow over to here.
Yeah.
So there will be current flowing this way. And let me just double check the minus sign here. Oh,
resistor or a resistor in
Excuse me?
that? I thought on the quiz for some reason that if we had a capacitor and a inductor, that it would stay fully charged.
Capacitor. Yeah, to stay fully charged.
And that a resistor and a inductor would have a slower loss of charge over time. Am I wrong with that?
It depends on how it's set up. In a situation like this, and I do need to change something there. Because I'm the capacitor is not going to stay fully charged in the sense of it will charge is going to move from one plate to the other. But I'm trying to think of one of the
LC circuit.
Yeah, the LC circuit, the inductance capacitor, capacitance starts charged.
Is that one of the flash ones?
Uh-huh. Current flows forever. This is the current flow there with the
Yeah.
LC.
Oh, current flows forever.
Yeah,
Okay,
yeah, that's what we're deriving.
gotcha.
So we're actually working, so this time we're working with you and and you're not ahead of us.
Is that a good feeling or not?
Yeah.
Okay.
It's a lot better than not knowing what we're doing.
All right, so I got a positive and negative charge here. The current is going to be flowing
Okay.
clockwise. The electron's flowing the other direction. But what I care about is the direction of the current flow. So I'm going to do a voltage loop in the direction that I have here. I apologize for the misstep earlier. So when I go across the capacitor, this is going to be something positive here. So this is going to be whatever the charge on the capacitor is divided by the capacitance. Because if you recall, capacitance is charge divided by voltage, and therefore voltage would be charge over capacitance. Minus L di dt. And this is the current flowing through the inductor. It's equal to 0. Okay. Part of my hesitation here and why I keep looking at the notes is that I've done this derivation many times before, and there are certain things that I screw up the minus signs a lot. Not as many as I used to, but I still screw up the minus signs, and I just wanted, once bitten, twice shy. So let's think about this. So first off, the relationship between current and charge. What is the relationship between current and charge? So we have two things that we need to worry about. One is the relationship between current and charge, and the other is the relationship between charge on the capacitor and current flowing through the inductor. So let's first do the relationship between current and charge, or what's the definition of current?
And then what's the formula for current?
Yeah.
Isn't it Coulomb per second, or Coulomb times second?
Current is Coulomb per second. So what would be the formula?
Q over T.
DQ or DT?
dq over dt. So this basically would be the second derivative of this charge that is flowing through the inductor. So this is QC over C minus L T squared QL dt squared. These charges are not the same though. The charge that is flowing through the inductor is the charge that has left the capacitor. QC is the charge that's still on the capacitor. So QC plus QL is some constant. I guess I probably shouldn't use C for that.
Okay.
If I take a derivative here, I get dqc plus dql is equal to 0, or dqc is equal to negative dql. So this equation now becomes, well, it's equal to 0. It now becomes QC over C plus L dQC over dt squared equals 0. That's right there. So the question is, what is the function that can satisfy this equation? What kind of function has it so that my second derivative would somehow cancel out the initial function? And in theory, you would have seen something similar to this in 151 or 251.
Be like a sine or a cosine.
Yeah,
function.
sine or cosine.
Since we're doing QC here, this is the charge on the capacitor and it starts fully charged. Cosine makes more sense at this time. So if we let QC equal some amplitude, let's call it Q initial, Q sub 0, cosine of omega t. Then my second derivative with respect to time, well, my first derivative would be Q naught omega negative sine omega t. And then my second derivative with respect to time, negative Q naught omega squared cosine omega t. And now we plug in to our equation over there, and we have 0 equals Q sub naught cosine omega t minus Q naught L omega squared cosine omega t. And quick check, make sure I didn't leave something off. So I got the L's comes from my equation, and the rest of it should be that. Bringing one over to the other side and getting rid of stuff, so the Q naughts go away, the cosine goes away. Oh, I lost something. That's over C. So I have L omega squared is equal to 1 over C. Omega is equal to 1 over LC, omega squared. So omega is the square root of 1 over LC. So what's going to happen here is that we start out with all this charge, all this positive charge on the positive plate. We set it loose. There's no resistance. It's not going to degrade anywhere. All that the positive current's going to flow through the loop, hit the other side of hit the negative side, so they'll switch sides, and then it'll all flow back, and then flow the side that side. So these will flip back and forth. And the time it takes to do that, well, let's dip back into our simple harmonic motion stuff. I know that omega is equal to 2 pi times the frequency. Frequency is 1 over the period. So my period is 1 over the frequency, which would be 2 pi over omega. So 2 pi times the square root of LC. So we didn't make a chaos error. And that's how long it would take for the current to show up on the other side, onto the other plate, and then, or better wording, it'd take for all the positive charge to show up onto the negative, the formerly negative plate, and then same amount of time to go back the other way.
There's alternating back and forth the whole time, basically.
Yep, goes on forever.
Okay.
Until you mess up.
I was about to say something like until something has a contact or something.
It's ideal.
Yeah.
I do need to amend one thing I said here. This is the time it would take for the charge to go to the other plate and back.
So that's just one cycle, not a full cycle, I guess, back and forth, just like one side, other side. One side is 2 pi square root LC, that's the time, I guess.
That would be for the positive, so for all the electrons to show up over here and then back over here again.
Okay.
That would be the period.
That'd be full. Okay.
Because after one period, you should be back to where you started. So the time it takes for it to get to the other side alone would just be half that, or pi square root of LC.
Okay.
Fun with inductance. Let's talk about units. I know that the voltage is equal to negative L di dt. So we can at least play around some with units here. So the units of voltage are
Volts.
that's units of inductance, units of current,
Amperes.
or change in current. Units of change in current?
Just coulombs.
No.
Ampere.
Amperes. 3 amperes minus 4 amperes is still amperes. Units of time, or change in time.
Eons.
True, let's stick with SI just for the fun of it. However, not, it is correct. So what we end up here are the units of inductance would be the volt second per ampere, which of course is the Henry.
Was that his first name or his last name?
I believe it's his last name. Otherwise it'd be called the Hank.
Right.
You got too many Henrys.
Now, for you people who play word games, there is an inverse inductance as well, with the unit of, I've never actually heard anyone pronounce it, I usually pronounce it irna, but it is a legitimate word. So if you play Scrabble, Words with Friends, whatever it is, this is a real word. Just like ohm is a word, and the reciprocal of resistance is the mho, as units of mho.
You can use that Scrabble though.
I'm
Use
gonna-
it, but not.
I'm gonna try that one.
I know, right?
Words with Friends, I have done irna before. I don't know if I've done mho or however it's pronounced.
Solid 20.8 point word right there.
All right, questions? Okay. So let's talk a little bit more detail about oscillating currents. Because what you're really dying to do is more calculus. You'll eat your minds. Let's do more calculus.
Did you say oscillating currents or alternating currents?
Alternating. What was the other choice?
You said
You said, I
oscillating.
thought you said oscillating.
Yeah, that's what I heard. Same.
I'm not sure if there's a difference really in the context.
Okay, I just,
Officially alternating current, but that's something that's oscillating back and forth.
Yeah.
So I stand by whichever word I use. So if I have a cosine curve, so let's just say cosine of theta versus theta. And so I've got a basic shape like that. Where that's pi over 4, pi, 3 pi over 4. Try that one again, pi over 2, pi, 3 pi over 2, 2 pi.
That's a full.
So if I found the average value of this cosine of theta over the full 2 pi, what would the average value be?
0.
Okay? So when I am actually trying to talk about alternating current, it doesn't really make sense to talk about it in terms of, well, the average value is 0, so we have no current flowing on average. When there's obviously something, current's not flowing for only a brief moment as it switches direction. So they need to somehow come up with a way of averaging this, which actually makes some sense. And so they came up with the root mean squared, the RMS value. And so the way you figure it out is you basically do it in reverse order. First you square it, then you find the mean, and then you take the square root. So first we square it, so we square cosine of theta. We find the average of that from 0 to 2 pi. We can make it more generalized than this, but I think this is sufficient for what I want to get across here. And then we'll take the square root. Is this a common calculus problem that you?
Very similar.
I mean, I can stop here and just give the answer, or we can work through it. It depends on if you do this in your sleep.
Go right ahead. Give us the answer.
So how do you find the integral? Well, the bottom one, why don't I do that one and you guys take the top one? How do you find the integral of cosine squared theta?
2 cosine.
Cosine over 2.
Say it again?
3 cosine over 3, or no?
No, let me get a break.